Good morning, students. Let us continue on the point where we stopped last time. If you remember, on the previous section, we have seen the working principle of the generator. And under this, by taking the elementary generator principle, I showed you how the DC generator produces a DC current or voltage at the terminal, and especially with the help of split ring commutator, how to convert the internal generated AC signal into DC signal we already addressed in our previous section. And we have also seen how the magnitude of the induced voltage inside the generator, and we said the internal generated voltage EG is going to be K phi N, and the K prime is ZP by 16A, where A is the number of paths in this conductor and Z is the number of conductor in our armature, and in our machine P is the number of pole. That we have seen, or we derived this in our previous section. And we also attempt one example, and we'll proceed as a second example. Second example says that a wave wound armature of 4-pole DC generator is required to generate an EMF of 220 volts when revolving at a speed of 900 RPM. Calculate the magnetic flux per pole required if the armature has 144 slots with 2 coil sides. Per slot, each coil consists 4 turns, it says. Now, what are givens? What are the givens? The givens, already the internal generated voltage is given, EG how much? How much is EG? It is 220 volts. And coil is given, coil how much? 4 is given. And number of pole, machine has got 4 pole. And speed, it is 900 RPM is given, 900 RPM. And slot of the machine is also given, 144 slots. I think these are the given parameters. And calculate the magnetic flux per pole required if the armature has 144 slots with 2 coil sides. Required is flux per pole. Now the machine is a 2 coil side sense. When we see the armature winding of the armature, it looks like this. We call this is coil side. So when we place this in one slot, this is going to be placed in another slot in another pole. If this is under S, this is going to be under N, it means. So we call one coil has 2 coil sides. This is a coil side. Okay? So having this concept, let us try to attempt. So the required one is flux. We know from the EMF in this equation, K phi N. So our N, our phi, is going to be EG divided by K prime N. K prime N. The question is, what is K prime? We have to know these parameters. Okay, we have to know this. What is Z? We don't know directly Z. P is already known and A is already known. We already told the path. The path we already told. So it is a wave winding. So if it is a wave winding, A is equal to P. This A is equal to P. So we know A. So what is that is a question. What is that is a question. Now from our given, we are given that slot is already given and number of conductor per slot is given, and we already told that it is two-layer coil side. So our Z is going to be 2 coil times slot. We can use it. So this, what is this 2? Because one coil has 2 coil side. Let me erase this, sorry. The winding most of the time it looks like this one terminal, this another terminal, and which is connected to be the commutator normal. So this is called coil. It has 2 sides. This is a hole, it is called coil, and it has 2 sides. So the overall conductor in our machine is going to be 2 times the number of coil times the number of slots. So 2 times our coil, how much it is? We told them it is 4 coils are there, and each coil how many conductors it has having? 144 conductor. Therefore our Z is going to be 1152 conductors are there in our machine. Now once we know that, we can directly go to the EMF equation. So phi, it is Eg divided by K phi N, we say. So our K phi ZB by 60A, we know this. So my Z is 1152 times my P, how much P? Number of poles? All 4. And what is A? A is going to be P, which is equivalent to P times 4. So this is our flux. This is our K prime. Now flux is going to be, we have to calculate this, and Eg is already told, how much is it? 220 times divided by K prime is this much. How much is much? We have to calculate it and get it in the result. Let me calculate on my hand calculator. So 1152 divided by 60, it is 19.2, it seems 19.2. So this is going to be 19.2. So 90.2 times 900 RPM. This is our flux. So flux is going to be, according to my calculation, 6.366 milliwave. It's going to be the value. That's how we have to calculate the required parameters from the given parameter. Okay, let us proceed. There are a number of examples are there, 4 examples are there, which we are supposed to do it at your home. So you check yourself and try to calculate the required parameters for the given equations. The next point is equivalent circuit of the DC machines. So under this, DC machines have got two major parts: the rotating part, or what we call it the armature, and the stationary part, the stator, or where the field winding is existing. So when we say the equivalent circuit, we are going to just see the equivalent circuit for armature, the rotating part, and the equivalent circuit for the field windings. Of course, here, when you say the armature circuit, on the armature, as you remember, windings are there, core is there, and shafts are there, so many things are there. So when we consider the equivalent circuit, we are going to model the winding only, because that is the one which is having an effect on the induced voltage. So under this, the armature circuit is going to be modeled with this. What is this? Here it is EA or EG. Sorry, friend. The armature circuit, the whole armature circuit, is represented by voltage source. It is because its induction is going to be take place in this, we say. So we can represent it as a voltage source. And the winding of the armature is neglected, the L part especially, and the resistance is going to be modeled as armature resistance RA. And some references, you may consider voltage brush drop. The voltage which is going to be dropped under the brush can be represented with a voltage source. It's like opposite to the current flow, just to indicate the drop, So with voltage drop in the brush can be incorporated as a circuit, as a model in the model. Therefore, armature as a whole represented with armature winding resistance and induced voltage. Here, how everything is included in this? Basically, this equivalent circuit of a DC machine is coming from the Thevenin equivalent circuit of the armature. Thevenin equivalent circuit, I think you remember on your fundamental courses. It is a Thevenin equivalent circuit representation normally. And when you come to the stationary part of the field winding, we have coil, which is going to be represented with LF, and we have resistance of the coil RF. Here, when you compare the number of turns and the cross-sectional area of the field winding with an armature winding, this has got a significant effect. That's why we represent LF in stator and neglect here in armature winding, because their effect on the armature compared to the stator or the field winding cross-sectional is also very few, and its effect is very less. That's why it's neglected. So the coil is represented as RF, LF, inductor, and resistance RF. And in order to control the field or the IF current or the field current, we usually introduce adjustable resistor, RF. RF adjuster represents an external variable resistor to control the flux inside the machine. Sometimes you may get the RF and the RF adjuster can be lumped together and represented as one variable resistor. Therefore, in a simple approach, the equivalent circuit for DC machine can be represented with this representation: field and armature. And if the machine is a smaller capacity machine, sometimes we may drop this V voltage brush drop. So if voltage drop is neglected, simple circuit for DC machine will going to be looks like this. This is a field winding representation equivalent circuit, and this is the armature winding representation. We will use this circuit representation in our future application. That's why I need to bring it here. And the next point is types of DC generator. Now we have seen the construction, principle of operation, generated voltage inside the DC generator. Then now let us come to discuss on types of DC generator. So broadly, DC machines can be classified as separately excited, self-excited, and permanent magnet generators. This classification basically based on their excitation principle. When we say separately excited, the field is when the shunt windings are supplied with different source. In this case, they are supplied from separate sources. That's why the name called separately excited. But in case of the self-excited, the field and the shunt winding or the armature winding is going to be supplied from the source, the same source. The name called self-excited. And permanent magnet is a special type where the magnet or the flux is supplied from the permanent magnet. It's not supplied externally from the same source or different source. It is generated from the permanent magnet. Again, self-excited DC generator can be classified into three: shunt, series, and compound. Shunt means, see here, if you see a classification based on the DC machine, this is the field, this is the armature, right? Now the field needs separate source here, and the armature needs separate source. Therefore, it is called separately excited. Separately excited. Now, when we come to this field and armature, they are supplied with one voltage. They are called shunt. Here, the armature and the field are connected in shunt or in parallel. That's called the shunt type. And if the armature and the field are connected in series like this, armature and the field in series, it is called series type of DC generator. If they are combined, here armature is there, one field winding is there, another series field winding is there. So now it is connected in different, we call it short shunt type, we call compound. When the armature and the field are connected in compound form, the compound generator itself can be cumulative or differential. Cumulative can be long and short, differential can be long and short. Here are the connections. Here, short shunt type, for example. Now in this case, these are in parallel, these two field windings are in parallel with armature. It is called short shunt. And here it is in parallel, but the way it is connected, now this is going to be, it seems in series, these two field windings are in series but in parallel to the armature. It is called long shunt. It is called long shunt. And the differential and cumulative compound, this connection is here. I think you can understand from the connection itself. And the direction of the arrow, I think you will understand what the difference between generator and the motor now. If the current is flowing outside, it is a generator. If it is flowing inside, it is a motor from the principle of energy flow. So this is the way we can classify DC generator. We'll see them in detail one by one. Now, based on the excitation, DC generators can be classified into separately excited and self-excited. When we say separately excited, the field coil are energized from an independent external source. We need two different supply means. Now, it is called separately excited. But when we say self-excited, the field coils and the armature coils are going to be supplied from one generator itself. One generator itself. There is no need of having two different supply. Due to this, it is called self-excited. For the excitation purpose, it will provide the voltage from itself. This self-excitation, like I said previously, it is divided into series, shunt, and compound generators. Now let us see what a separately excited is. Like I said previously, in this case, the field is going to have different supply VF, and the armature is going to have different supply VT. I mean, different output voltage. This is a supply, this is an output voltage, V terminal. So, if you write KVL for this armature, obviously VT is going to be IARA minus IARA, or this is usually, now since I'm talking about generator, you can say EG, generator voltage. So this is simply KVL form of the circuit. In this case, the load is going to be connected here on the armature, therefore IA and IL are the same. Sorry, IA and IL are the same. They are the same. Therefore, IA is equal to IL. And when you come to the field winding, see this, the IF field current is going to be VF divided by RF. VF divided by RF. So these are important questions what we need to understand or know in our separately excited DC generators. And the power developed by the generator power, this is EA or EG times I. Power developed here as a generator, it is internally generated times current. And power output given to the load is going to be VT times I, the simple relation. So we can calculate this by the given formulas. So having said this, let us see the example for this separately excited DC generator. So in this case, a 25 kilowatt 220 volt DC separately excited generator has an armature resistance of 0.1 ohm and a field resistance of this much, 110 ohm. Calculate the power delivered in the armature when it delivers its rated power, it says. So what is given? Now what is given? Power is given, output power how much? 25 kilowatt. And terminal voltage is given to 20 volt. And what is given? Armature resistance is given how much? 0.1 ohm. And field resistance is also given how much? 110 ohm. And it's asking what is the power delivered. Power, we say that it is EG or EA times IA. And what do we know? We know that in the generator, generated voltage, or from the equivalent circuit of the generator, VT is going to be, EG is going to be IA RA. We know this from the equivalent circuit of the generator. Now, again, we know from the equivalent circuit IA is equal to IL, which is equal to P divided by V. Now, if you see the terminal, from the equation, it is a terminal voltage 220 volt, separately excited. It is a separately excited. Therefore, I or IA, I can say 25 kilowatt divided by 220 volt. Therefore, IL is how much? You can calculate it. So it's around 113.64 ampere. IA. Why I need IL? Because I want to know power generated, which is EG times IA. Now, IL is going to be IA, I said, so I came to know IA. What is remaining? EG. What is remaining? EG. So what is EG? Internally generated voltage. From the equation we know it is VT IA RA. Now we know VT. How much it was? 220 volts plus. IA how much we got? 130.64 times what is RA? 0.10. Therefore, EG is going to be how much? 231.634 volts. This is the internally generated voltage. What is remaining? Power generated. It is EG times IA. This is generated voltage. I mean power generated. So PA is going to be EG generated voltage times armature current. How much is 231.364 times how much? IA 130.64. Therefore, power generated is going to be 26.292 kilowatts of energy can be generated by this generator. That is what it is asking. The power developed in the armature is going to be how much? 26.29 kilowatt of power is going to be generated. So for next, we'll try to attempt for the second example. Second example says, it's already given with the graph, a separately excited generator when running at 1000 RPM supplies 200 ampere at 125 volts. What will be the load current when the speed drops to 800 RPM if IF is unchanged? It means the speed is dropped to 800, but IF is the same. What is IF means? The flux inside the machine is the same, unchanged it says. So given that the armature resistance is 0.04 ohm and brush voltage drop is neglected. So what will be the load current is what it is asking. You try it in your home and we'll try to attempt it here in class next. Thank you very much for listening.